मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, my dear students, we are now going to start 34th lecture in the series of mechanics of metal forming. If you recall back, we started the simulation method in metal forming called as finite element method. The basic concept of finite element method we started. So last time, if you remember, we covered the solving equations, basic solving equations. We also covered the basic equations for nodal variables, how do we have, then how one has to choose the right elements, the shape function and all that, and including two dimensional as well as multi-dimensional elements, element properties we considered, and we could also see while solving, getting solution of the matrix solution and solving the integrals that involved in partial differential equations concerning finite element formulation. Then we could see the nodes and integration point related issues, and then also certain design rules concerning mesh formation, how do we mesh the whole domain, and the meshing algorithms and the issues related to the advantages and disadvantages with finite element method when we incorporate at the very early stage in design process. We could see these issues. Okay. So as I told you, when we come to the designer point of view, we could see that a FEM expert is required along with a solid modeler designer, and there must be coordination between these two fellows. So we would start from that last lecture and we will continue this concept further, and we will then first introduce some basic problem today. So hopefully you are now aware of those basic concept, and let us start. As far as FEM development is concerned, and then the commercialization of those development mathematics in the form of softwares are concerned, I would like to inform you that the Control Data Corporation was the first company who sold a commercial finite element software way back in 1964. You can at that time there was no preprocessor, that means there was no mesh generator available. So engineers had to prepare data element by element and node by node manually, and only linear problem could be handled at that time. Nevertheless, it represented a breakthrough in the complexity of the problem that could be handled at that time. And then in 1980s, introductions of workstation when came, and that was the Citra, the company Circa, Circa company brought several breakthrough advantages when the workstation was introduced. and interactive graphics was then practically available by the time of computer power as well. To solve problems on a dedicated basis was then that time available around 80s. And then finally there was introduction of personal computer, and that was quite powerful enough to run these finite element softwares provides, and that provides extremely cost effective problem solving. So you will come to know that the development of computers technology, especially in terms of speed and all compactness is related, it occurred almost simultaneously as the development of finite element methods and all those too, because there was a pressure to have some machine that helps the fast computation. So that become around 80s and onward, and then that time the leading commercial software where if I remember that time it was Abacus, ANSYS, SDRC ideas, then RASNA, MSc and Nastran physics based FEM was there, etc. Now one can generate very complex geometries at either the component or assembly level with the help of computer aided design software or solid modelers. Like one can choose the solid edge, a solid modeler today very popular. Also we can generate nowadays automatically the elements and nodes, that is possible with the automatic mesh generators. By just merely indicating the desired nodal density. So softwares are also now available that work in conjunction with solids to generate structural topology, shapes or size, etc. As well as the non-linear analysis including contact, large deflection and non-linear material behaviors are also routinely it is addressed nowadays. So why I am discussing all these things, that one has to realize the scope of FEM. That is how I am telling you these details, which is apart from the usual the talk of the basic of the finite element method. As far as the future of finite element is concerned, if you look today and since early 1970s till now, it remains the dominant method. Finite element method is still a dominant method, and software components such as preprocessors, solvers, post-processors, etc. can be used in a modular fashion now, in a module form now it is available, so that the improvement in the diverse area can be rapidly assimilated. The major innovations in technology, for example, p-adaptive finite element or h-adaptive finite element method and combined p and h adaptive finite element. These often takes a decade to move from academic to commercial practices. So improved iterative solvers, meshless formulation has also appeared, better error indicators and special purpose elements is the list of current research area nowadays. Improved efficiency achieved by computer technology advancement such as parallel processing will surely occur in finite element method as well. The integration of CAD and computer aided manufacturing and finite element method is still an existing and very exciting and important part of the engineer's toolkit. So this is what the future is to be there, and the future of finite element method is very bright. As far as the metal forming is concerned, it has almost every area it has been entered. Now these softwares, if you name the software that is popularly used for metal forming, like your LS Dyna, all modules, then your deform, like, and many other softwares, as I have already told you, are now popular, and the people are solving with the help of these softwares. So if we let us see it again, for those who came late, let us revise it, and let us say why finite element method. If suppose now if you want to again at this stage want to know, first thing I told that it helps in design analysis. So when you use the hand calculators, experiments for designing etc., and computer simulations, so it helps there. Secondly, the finite element method or finite element analysis is very widely applied computer simulation method, and especially in engineering it has become very popular nowadays. And the last one which I would like to mention, that it is the method which is closely integrated with computer aided design and computer aided manufacturing. So whatever you design on the basis of analysis, you make sure and you freeze the design. Once you have freeze the design on the basis of analysis, and then certainly the design has to be made it. So you go into the domain of manufacturing. So it can be easily linked, because it is the data that is available in the FEM also, geometrical data, topological data, then in CAD, and then the same can be clubbed with manufacturing like CNC machines and all those things, and many other applications. As far as the application is concerned, looking into, so for the discussion, as I told you, the applications are valid in mechanical engineering, all area, aerospace engineering, civil engineering, automobile engineering, then structural analysis like static analysis, dynamic analysis, linear, non-linear analysis of all kind. Then the thermal and fluid flow problems, electromagnetics, geomechanics, biomechanics, and many others. The time will come, because the day by day the scope and application of finite element method is getting larger and larger. So look at this figure. This shows a modeling of a gear coupling. So you see it's a mesh. You can analyze on the basis of finite element method here. So as I told you, the very first the FEM application 1943, when Courant used the variational method. Then in 1956 Turner and Clough, Martin and Top started with the stiffness K matrix application, and then 1960s Clough, which introduced the finite element for the plane problems. Then in 1970s applications on mainframe computer was introduced, and then 80s, as I told you, when the microcomputers and preprocessor and post processor concept came, then it becomes very accelerated, and in around 90s the analysis of large structural systems has now been possible. So if you look into the finite element method in structural analysis. Why I am discussing structural, I am not jumping to metal forming is the reason, is one reason that the structural analysis are almost static. So if you are able to understand the static one, and then it would be easier for you. That's how I am. Let us see the finite element method, a procedure. What procedure should be there? If you now recall back whatever we discussed earlier in the last two lectures. So if for the structural analysis, how can it be put together? So first, as I told you, you divide the structure into pieces. So, and that is the discretization are the elements and nodes, and then describe the behavior of the physical quantities on each element, and then connect or assemble the element at the nodes to form an approximate system of equations for the whole structure, as I told. Then solve the system of equations involving unknown quantities at the nodes, that is the displacement if it is, and then you calculate the desired quantities, that is maybe strains, stresses at selected elements, and that is how the method we have discussed. The elaborated 7 stage method was also discussed earlier. So look at this figure. This is what a can drop test, a finite element for a can, which you use it as for our soft drink and all those things. So this is what's the analysis, and that is for drop test. So there is a plane on which the can has to drop, and you see the meshing. Here it is used as all quadrilateral elements. So usually in crash analysis or drop test, we go for quadrilateral element. So this is what I wanted to show you, a usual mesh for this case. So now you see this figure. This is the same last time I show the gear. So this is the FEM model for a gear teeth. If you take one teeth, so you see the nodes and elements, how the nodes and elements are there, and you will see this is again a quadrilateral element having how many nodes? If you see one quad, so there are 8 nodes, right? So the quadrilateral, it's a what kind of shape function? It is a linear, quadratic, or what kind? So this is what's the meaning of. So this is one element has 8 noded quadrilateral elements, right? So you see the distribution. You can make it further finer, but please remember that when you make this mesh as very fine, then the number of elements will increase, and accordingly the computational time is also going to increase. So these are some of the issues. So again, if you recall, you can solve it the pre-processing, where you build the finite element model and you put the loads, constants and all together. Secondly, then you use some solver, like you assemble and solve the element system of equations. And thirdly, after solver you get results of post processing. So that is the sort of display the result on the in a color way manner, so that you can conclude something, a relevant thing, a for application. So as I told you that there are many softwares available, commercial software. The ANSYS, which is a very general purpose PC based orchestration software, then SDRC Ideas, which has a complete CAD CAM and computer aided engineering package. So computer aided engineering is actually where you have computer modeling, then and a finite element method altogether. So that's we call it the computer aided engineering. Nastran you all are aware of. That's the general purpose FEA on mainframe station. Then Abacus for non-linear and dynamic analysis problem. Cosmos is also very popular, which is a general purpose finite element analysis package. Algor, it's a PC and workstation based FEM software. Patron, it has pre-processor and post-processor only. The Hypermesh, as I told you, it is a Altair engineering module, and it is a very generalized software for creating any kind of mesh, any kind of mesh. It has automatic creating capability as it has a manually creating capability as well as, and it has both pre-processor and post-processor. The solver you have to choose from some other work. So, and very popular the LS-DYNA 3D. So, that is popular for crash and impact analysis, very popularly used the LS-DYNA one. So, these some of the commercial packages, and so as far as if you go for any such thing, let us look at this figure. This figure shows a container where under the loaded condition how the stresses and strain appears, it is showing here. So that means if you see the so much colorful things, so you will, where the red lines are there, red regions, it shows that that area is very much stressed. So just looking after one can know, and then you can think of how to avoid this heavy loading of the stresses, all that. So any thing that you require in FEM, that you must know the behavior and uses of each type of elements covered so far whatever has been made. And please beware of the limitation of the finite element method, because please don't misuse the FEM. It's a numerical tool, so one may misuse, that will lead to a very difficult and odd situation. So looking into this, as I told you, there are the solution concerned with the set of simultaneous equation and you require to solve it. And as I told, the simultaneous equations requires matrix algebra. Okay, so to introduce it, I would slightly few slides I would take it to explain you the simple matrix algebra. So look at this set of equation where the linear system of algebraic equations are given. So this equation number 1, where you have a11 x1 plus a12 x2 plus and so on, a1 n xn is equal to b1, second equation a21 x1 plus a22 x2 like that is equal to b2, and so on. There are set of equations where x1, x2 and xn are unknowns. So if you convert this set of equation into matrix, so if how do it appear? So one can write down the matrix form of this system of algebraic linear equations. That means capital A x is equal to B, where A relates to a matrix, that is Aij, and it is expanded Aij matrix. The elements are written as shown in equation 3 here, right? So we represent in this fashion. So this matrix, A matrix, is A11, A12, one n like, and then a last one a n1, a n2, a n3 and a mn like that. So this is the m multiplied by n order of the matrix, capital A. And X is another set of matrix which is xi elements. So it is a column matrix. So the elements are x1, x2 and all those xn, and B is also a column matrix. The elements are having bi components. So that is b1, b2, b etc. and bn. So A is called a n by n is square matrix, and X on the other hand, X and B are the column vectors of dimension n, right. So that is the very basic of matrix algebra. So row and column vectors, one can write it like here. So for an example, row, the vector V can be represented, which is a row vector, as v1, v2, v3, and W, where it is a column vector, it can be represented the elements as w1, w2, w3, which is shown here. So if you recall the matrix addition and subtraction for, say, for two matrices A and B, where both of the are of the same size, that is of course m multiplied by n size. So the addition and subtractions are defined as usual. You all have studied at very basic at 10th class level. So the C mat will be the, if it is addition, that is A, matrix A plus matrix B, with the elements of the C matrix, that is Cij, would be equal to the elements of Aij plus elements of Bij. So the element would be added. Similarly, if it is a matrix D, which is the difference of matrix A and B, so that can be simply correlated as Dij would be equal to Aij minus Bij. That is the simple definition and revising for you. So scalar multiplication, if you look at, so that means if you multiplied by lambda to a matrix A, so you multiply each element of the matrix A with the scalar quantity. That means lambda A would be equal to, within the matrix, each element lambda Aij. And similarly the matrix multiplication, it has a, for two matrices, for an example size matrix A of size L multiplied by M, and the matrix B of size M multiplied by N, the product, that is kept matrix A matrix B, is defined as C. That means matrix C is A multiplied by B, where the elements of C would be what, that is Cij is equal to the summation over I is equal to 1 to, say, if it is M, right. So that is A I Lm and multiplied by B Mn, right, Ij, Aij multiplied by Bij, alright. So I varies from 1 to L and J varies from 1 to N, right. So the I variation of over the summation is I is equal to 1 to M, therefore. So please note that the matrix multiplication, that is A multiplied by B, is not equal to B multiplied by A, please remember. But if you have AB multiplied by C, that may equal A multiplied by B C. This is what is called as the associative rule. So this is just to recall you and refresh you. If you take the transpose of a matrix, what happens? So in case of transpose of a matrix, if suppose the matrix A, which is Aij, then the transpose of capital A is in fact we write it is At, and that is equal to elements A Ji, right. So that is the transpose. So elements of A is Aij, so the transpose the element would be Aji, and one has also to remember that matrix AB transpose would be equal to matrix B transpose multiplied by matrix A transpose. So this is what about the transpose of a matrix. Similarly, the symmetric matrix, when we call a matrix to be symmetric, so a square matrix, say n by n matrix of A will be called as symmetric if the A is equal to the transpose of its matrix, that is A is equal to A transpose, or Aij is equal to Aji, that is all, right. And the unit or identity matrix, you know, where the all diagonal elements are 1 and all other elements are 0, that we call it as the unit matrix. That means if you multiply a matrix by a unit matrix I, then what you will get the result? For an example, if you multiply A and then a unit matrix I, then it will be equal to A multiplied by I x, that is x is equal to x, right. And then another thing is of very important, where the determinant of a matrix is obtained. So if you recall, the determinant of a square matrix capital A is a scalar number which is denoted by determinant det A, we represent it by det A, right. So for a 2 by 2 matrix or 3 by 3 matrix, their determinants can be given as here, that ABCD is equal to AD minus BC, right. So that is what is given here. And similarly, the determinant of the matrix like 3 dimensional 3 by 3 matrix like A11, A12, A13, A21, A22, A323, A31 and all those things are there. So it can be written as here, which has been shown. That means A11 multiplied by A22 multiplied by A33 plus A12, A23, A31 plus A21, A32, A12 minus A13, A22, A31, and likewise this is shown here. Okay, so that's the your determinant of a matrix. Similar matrix, if you recall, a square matrix capital A is a singular matrix if the determinant A, if it is calculated, it comes out to be 0. That indicates problems in the system, that is a non-linear solution, or we call it as a degeneracy problem. So if the matrix becomes square, that means determinant of A becomes 0, then it is taken as a great problem, and you have to resolve that this does not occur while solving a system of equations. So because it gives non-unique solutions, which is we never expect. And then we also come across the matrix inversion. So matrix inverse, so for a square and non-singular matrix capital A, determinant where the determinant is not equal to 0, that is correct. So its inverse, that is A inverse, is constructed such a way, in such fashion that capital A multiplied by A inverse will be equal to A inverse multiplied by A, and that would be equal to identity matrix I. So it should be constructed in that way. So, the cofactor matrix C of matrix A is defined as Cij, and that is equal to minus 1 raised to the power I plus j multiplied by Mij, where Mij is the determinant of the smaller matrix, which is obtained by eliminating the ith row and jth column of capital A. Thus, the inverse of A matrix A can be determined how much? If you recall, that is A inverse would be equal to 1 by det A multiplied by Ct, that is the Ct is the transpose, and then one can show that A P inverse, that is the matrix A multiplied by matrix B, and this whole together the inverse would be equal to B inverse multiplied by A inverse. You can show it, right. So, these are the some of the things just I wanted to recall you. So, now let us take a simple example, right. So, if we take a simple example, this is what is the example 1, where the matrix is given as A, B, C, D, and let us calculate the inverse of this. So, how it would be? So, the inverse must come as 1 by AD minus BC multiplied by the matrix having a element D minus B minus C A. One can check. So, you can check it, that is A, B, C, D inverse. If you multiply it by the matrix itself with the element, so A, B, C, D, and if you expand, you get the identity. So, that is the identity matrix, you get it. Let us take the second example. So, example 2, where the 3 by 3 matrix is there, and let us calculate the inverse of that. So, by definition the inverse is 1 by 4 minus 2 minus 1 multiplied by 3 to 1, 2 to 1, 1 1 1 transpose of this, and that results into 3 to 1, 2 to 1, 1 1 1. So, that is, and one you can check it. So, if it is checked, so you will find that what is there, and then you can calculate the determinant A of this, that is the A is a singular there, and then therefore the inverse is does not exist, right. So, one can get the solution of the linear system of equation using 1, and it can be expressed as the coefficient of matrix A, which is non-singular, that is x is equal to A inverse B. Thus, the main task in solving a linear system of equation is to found the inverse of the coefficient matrix, is it? So, that is the how things goes. And then as far as the solution technique methodology for linear system of equations are concerned, there are two methods, if you remember, the Gauss elimination method and another iterative methods are very popular. So, positive definite matrix like a square matrix n by n matrix is said to be positive definite when if for all non-zero vectors of x of the dimension n, the x transpose then matrix A multiplied by x must be always be greater than 0, then it will be called as the positive definition matrix. Note that the positive definition matrix are non-singular, right. So, differentiation and integration of a matrix one can now consider. So, when we differentiate, we often come across in partial differential equation and all those things. So let us see the differentiation and integration of a matrix. So let capital AT that has element A I J T, and if it is differentiated, so the differentiation is defined as d by dt A T. So AT is the matrix having elements A I J T, and when it is differentiated with T, we can write it as dt d by dat dt, and that is what is the daijt divided by dt, that is the matrix. And the integral, likewise the integral at dt is the integral aij t dt, that is the basic definition. So when we move in the larger problem, as I told you, you have to discretize it, the whole domain. Either you discretize as a 1D problem, so 1D problem means it is a line element. You can discretize it is a 2D problem, that is a plane element, and you can then also discretize as a 3D problem, that is called as a solid element. So here this figure shows the types of finite elements. So figure number 1 shows the 1D, which is a line element. Generally we come across the spring problem, truss problem, beam problem and pipe problems, etc. We can solve it considering the whole problem, either it is of a string, truss, beam, etc., of considering it as a 1D problem. When we come across like the plate bending and all that, or cell bending and all that, or membrane deformation and all that, we usually take 2D element, which is also called as the plane element. So if you look at this figure, the 1D line element has a basic element, has 2 node and 1 element in between. So that is a one line. Whereas in case of 2D, that is a plane element, you have 4 nodes and that is one node. So it's a square or rectangular in a rectangular 2D mesh. You may have a tri mesh also, that is a triangular one. The third category which is shown here is a solid mesh or 3D mesh, where this is also a called as the brick element. So this brick element has got total number of how many? 8 nodes, and there are 8 line elements joining them. So altogether a brick element has 8 nodes of linear in nature. So likewise, if you take the 1D case, the upper one, 1D line element, if you take 3 noded element, so 3 noded element will represent a what kind of element? You may say it's a linear, or so that's the, if you increase the number of nodes, so you are going to increase the order of the nodes. So one has, as I told you, the selection of the type of element is very important, and there are certain guidelines last time I discussed. So looking into these elements, a large problem consists of many such elements. If it is the case of say spring, truss, beam or pipe problem, we go for the 1D problem, and there is a number of such elements. Similarly, if it is a membrane, plate problem or bending of cell, etc., or a cell having a very high pressure deformation, so we go for the 2D problem. Whereas A three-dimensional problem we very often come across in metal forming, like extrusion, forging and all those things. So one can go either for the brick element, or one can also go for a prism element, right? So this is all what's the different application, it depends. So we would continue this lecture, and we would be taking few examples where we may start with the simple say spring problem. So to represent the first D, then we will move ahead with the 2D problem, and we will take up few cases where the three-dimensional stress meshes are used. Please remember that pre-processing is also very important. Pre-processing, if it is well done, then while you give it to the solver module, there is no stucking in problem, there is no error. So that's how the preprocessor, if proper conditions are selected, then it is also helpful to solver to solve it easily and without any difficulty and within a lesser time of calculation. So with this we would take up now the problems, basic problem 1D, 2D and 3D next time. By the time, I thank you all students for listening, and only thing is that you please practice, because if you do not practice you will be loser. So please next time you take up some of the see in the textbook what has been told to you. Some of the books, as I told you, there is a book, Reddy book, right? So Rao book, and there are many books one can refer for the fundamental of finite element method, and for different application, because this is limited only to the plastic deformation. So we would tell you the some of the popular books which is used, and also some of the popular softwares, commercial packages that utilizes this concept. We would like Deform is one of the popular software. LS Dyna is one of the popular software. Forged is one of the so there are many such issues we would be considering next lecture. So I thank you all.